So we'll get started. Welcome to this week's UTIG seminar. So today we are really glad to have Ian Hamling here for this week's seminar. So Ian got his PhD in School of Earth and Environment at the University of Leeds in the UK in 2010, and he worked at International Center for Theoretical Physics in Italy before he joined the GNS Science at New Zealand in 2013. Ian's research focuses on using satellite remote sensing to analyze tectonic and volcanic processes, and he was the recipient of 2017 Hamilton Early Career Award by the New Zealand Royal Society. So Ian, time's yours.
Oh, thanks very much. Yeah, thanks for having me. I apologize, my screen is on over here, so if I'm looking this way, I'm not trying to ignore people. It's just unfortunately my home setup. But yeah, again, thanks for having me. I'm sure Laura had some arm twisting involved there, but hopefully what I'll cover off is a range of stuff I've been looking at recently with a whole bunch of people, ranging from some more sort of volcano related problems through to then looking at some sort of larger scale tectonics on New Zealand, which obviously I've done quite close in hand with Laura. So New Zealand is definitely a challenging place to try and do interferometry. We've got a lot of interesting terrain. So in fact, in this picture, you can see we've got some very high mountains, which are often very steep. They've got lots of snow cover. We've got a lot of vegetation that also plays a lot of problems with radar interferometry. But fortunately, we've got quite an active plate boundary with lots and lots of different sort of versatile things that we can look at. So what I'll try and cover, I'll give a really brief overview of SAR and interferometry, because I'm sure many people are aware of the technique and more or less how it works. And then the focus will be kind of in two parts. One will be looking at some earthquake triggering of an eruption in Vanuatu, so in the Southwest Pacific. And then I'll afterwards move south to New Zealand and talk about a little bit about, again, some of the volcanics in New Zealand, and then this kind of work looking at the larger scale deformation that we've been trying to do. So SAR itself, so it's a remote sensing technique, and it works in the sort of the microwave band of the EM spectrum. The big advantage that it has over other remote sensing or optical remote sensing is because it uses microwave, it's able to send that energy all the way through the atmosphere and back again with very little loss of signal. Unlike optical satellites that rely on the sun, it means that obviously we can look through clouds or steam or ash for sort of volcano problems, whereas often in the optical space, then they are hampered by cloud cover, limiting sometimes their usage. So these actually bottom two are two examples from just after the Kaikoura earthquake in New Zealand. And again, you can see on the left-hand side, we had some really bad weather afterwards. So a lot of these optical measurements that people were using were basically completely useless. Whereas the radar obviously has this big advantage that we can see through the cloud. So you can use the amplitude imagery for looking at damage, and also then for using sort of the phase to try and get these deformation maps. I won't talk much about the bands, but typically we'd use, there's these three kind of bands that are probably most commonly used for interferometry. So these are X, C, and L. And this is just basically the wavelength of the signal, and different wavelengths are better or worse for different kind of processes. But really for New Zealand, unfortunately, we don't have a lot of L band in New Zealand, but that would be ideal because it's much better at dealing with vegetation. So how does it work in principle? So in its sort of base form, all we're doing is every time the radar satellite comes over the land surface, it takes an image and it measures both the phase and the amplitude of the radar signal. Now the phase really is just giving you a measure of the distance from the ground to the satellite. And so what you can do is then when the satellite comes over again, is you take the difference of those two phase signals, and you can measure essentially a coherent change in the range distance between the ground and the satellite. So in a very simple form, if you were to take two phase images, you see they're essentially completely random looking components. But when you take the difference, if there's been a systemic change across your entire scene, then what you can derive is these fairly impressive looking, well, impressive when you get good coherence, but these impressive deformation signals. So this is an example of the Darfield earthquake in 2009. And in this case, each one of these colored fringes is around 11 centimeters of motion, either towards or away from the satellite. Interpreting them is relatively straightforward. You have to assume some kind of zero level, and then if you were just to count these fringes in, you can then build up your sort of full displacement rate or displacement over the earthquake. So in this case, you end up with around 1 to sort of 1.2 meters of line of sight displacement. That's an interesting caveat. Is obviously, unlike GPS that gives you the full 3D vector, InSAR can only give you the one line of sight, which again is a limitation, but we can sometimes work around that problem. It's got multiple uses. So yeah, I think some of its power really lies in it's a very diverse technique. So we've obviously got cases where you can look for earthquakes. So an example of this was the Kaikoura earthquake in New Zealand, ridge crest. You can look at the interseismic cycle. So this is an example over Turkey, looking at sort of the long-term interseismic strain. And also now, because we've got more and more regular acquisitions, we can do sort of post-seismic transients following these sort of larger earthquakes. You obviously got volcanic deformation that we'll go into a bit more detail. So it's an example from Kilauea, where you can again track magma intrusions and magma migration through the crust. Another use which I won't talk to really is the amplitude imagery can also be very useful for tracking changes in, so especially actually I found in volcanic systems where you can track these kind of small scale changes. So this is again an example from Kilauea where you're able to sort of track the collapse of the caldera itself following during the 2018 eruption event. Probably more boring for lots of us is you can do kind of more anthropogenic kind of monitoring. So we've got in New Zealand, you can have cases where we've got gas extraction, we've got quite a widespread geothermal activity. So these are a few examples of a geothermal substance, and some of these rates can be very, very high, kind of tens of centimeters per year. Other areas that I'm not so interested in, but we're actively doing is working for sort of different councils around New Zealand and to do more urban monitoring. So looking at change in displacement along road networks or rail networks, and then that feeds into their kind of ongoing sort of hazard mitigations for their main infrastructure. And then the other big problem, but big signal in New Zealand is we've got lots and lots of landslides, especially through the South Island in the mountainous areas. And these are very, very pervasive across sort of large swaths of land. And so you can see in this example, basically everywhere you see one of these kind of little sort of spatial peaks of color is essentially a landslide varying in size from kind of hundreds up to, in some cases, a few kilometers long. And that actually, for other problems, which we'll go back to later, can become a challenge to deal with. So, kind of to the core of the talk, I'll start, as I said, with this example of potentially a triggered eruption in Vanuatu, and then before coming south towards New Zealand. So Ambrim is located within the Vanuatu Arc. So this is obviously New Zealand down here, so Southwest Pacific. And this is the arc I'm talking about down through here. Tectonic wise, it's controlled by, again, the Pacific, the Australian plate subducting beneath the Pacific. And as a result, then you've had the back arc extension along the length of this ridge, causing numerous volcanic islands. So most of these islands host an active volcano. Ambrim, which is this kind of triangular one in the middle, is one of the most active in the world. And that, again, has had eruptions in 2015, which I'll briefly talk about. And then there was another one later on in 2018, a much bigger intrusion. You can notice the convergence rates are quite high, order of kind of 10 to 12 centimeters a year. But there is this fairly significant drop in the center of the ridge where you've got the D'Entrecasteaux ridge that's kind of being subducted down into the plate, and that has then drops the total convergence over the area to around kind of a third of the overall rate. Interestingly, then in the same place on the back side of the arc, you've actually, because of that, you've had this development, this back arc thrust belt. And this actually has a fairly high seismicity of these kind of shallow thrust events up to sort of magnitude 7. So the island of Ambrim itself, so I said, is this small triangular shaped island in the center. It's around sort of 40 or 50 kilometers across, and it hosts this fairly large 12-kilometer wide caldera. And within that, we've now in the last few hundred years, you've had the development of these two kind of cones, in this case, Magma and Benbow. And this is really where the focus of the volcanism has been in the last kind of few centuries. There's an active lava lake within Magma itself, and that's been pretty pervasive again for at least the last 100 years. It's got a long history of activity, going back, the earliest records were from when Captain Cook was doing his world tour in sort of the late 1700s. And they had evidence of, they could see from the boat, but there was documents of there being heavy ashing and steam rise from the summit of the island. It's got these two rift zones as well, which we won't need to talk about too much, but this also has had where they have some of these big flank intrusions, similar to Kilauea, and then these kind of lava flows that come out at the tips of the rift zone. The eruption in 2015 basically came out where the star is showing. It's this sort of little black blob. So it was very small in terms of actually its sort of volume of the eruption. But it's actually, when we look at the deformation, it was actually a much bigger intrusion at depth. So again, just having a zoom in. So this is the lava flow we can see coming down from this new vent that opened. And this was the first kind of lava flow on the island since sort of the late 80s, so for around 25 years. What's interesting is there was no really precursive activity. The monitoring agency detected no increases in seismicity. Gas emissions were very static. And really, there'd been not much activity for the sort of the previous 2 years. And so the eruption itself came as a bit of surprise to the locals. And what kind of gained our interest is that when we started to look around, is that there was this magnitude 6.4 earthquake located around 15 kilometers to the south of the island, which preceded the eruption by around 30 hours. And for a different project, we were looking at trying examples of triggering eruptions, and that's kind of what spurred our interest, is to say, well, it could just be a coincidence, but we started to look to see whether this particular earthquake could explain the sort of the subsequent eruption. So this is the ALOS 2 interferogram covering that dike intrusion. So these are the two bits here are your two cones, and then this is the intrusion that came down that kind of southern flank. Again, in this case, each one of these are around 11 centimeter fringes, giving you around a total of 1.5 meters of the line of sight displacement. This is a pretty classical dike intrusion pattern, and you get this kind of nice sort of asymmetric butterfly, where on this side of the intrusion, the horizontal and the vertical components of the deformation add together, whereas on this far side, the vertical and the horizontal basically deconstruct against one another, and so you get a much smaller looking deformation pattern on that opposite side. So we do some fairly standard modeling. So this is using just a Bayesian inversion to try and estimate the geometry of the intrusion. So this is basically the results. So the data on the left, the model, and then what's left over is the residual. So this suggested around a 4-meter wide dike, 5 kilometers long, but it had a slight dip to the southwest of around 65 degrees. So what we do is we basically take that base geometry, and we sort of discretize it into one of these kind of variable opening model to get a better distribution of the actual where the volume was intruded. And this is just shown here. So again, this is dipping southwest 65 degrees. My brain's not managed to evolve into triangles yet, so I've still got the old square patches, which obviously gives you this kind of sheets in the wind. But then it does mean you do get some of these funny artifacts, obviously, where you get kinks. But having said that, what we basically find is we have this intrusion that was around close to 50 million cubic meters, and with a maximum opening of around 3.5 meters. there's some, what we can do is we can take some fairly simple analytic solutions, and we can look at trying to estimate the overpressure in that dike based on its kind of aspect ratio and its maximum opening. And if we do that with obviously some assumptions, we get an overpressure for the intrusion itself of around 7.5 megapascal. What's interesting is, as I said, the locals saw no precursory activity, so there was no indication of there being fresh magma being intruded into the volcano. There was no additional gas emissions being recorded. And then again, if we look at, this is an interferogram basically in kind of the month before the eruption, also 2 months before the eruption, and we don't really see any evidence of there being any widespread uplift or any sort of local intrusion. Another interesting thing is when we look at the actual deformation from the dike intrusion, we don't see any evidence of the two shallow cones. There's no evidence of sort of shallow deflation, suggesting that magma was sourced laterally. So it suggests that magma has come somehow from depth. Previous work has looked at gas geochemistry and seismic tremor, and that's indicated a deeper storage zone at sort of 3 to 4 kilometers depth. And this is pretty consistent. This is an example of the eruption in 2018, where we actually we saw this kind of deeper deflation signal as a big dike intrusion came out of down the flank. And this also worked out to be around 3 or 4 kilometers below the edifice. So we're pretty confident that that's kind of our storage zone at kind of this sort of 3 to 4 kilometer depth. What we also then looked at is looking at the sort of the post-intrusion deformation, where we see this kind of long-lived deformation or a long-lived substance pattern focused basically beneath where the intrusion was in place. And this again, when we model this deformation event, which occurred for this was about 2 years afterwards, what we find is, again, we estimate a depth of around 3 kilometers, with the sort of the focus of the deformation going on sort of just beneath where the sort of vent site was. So we've kind of made that assumption that this is where the intrusion was kind of fed from. But what I've just said, what we don't see is evidence of their new magma going into that system. So what we wanted to look at is how, if you've got this sort of stagnant body of magma sat there, how can we get enough overpressure in that magma body to cause the intrusion above? So this is when we started looking at ways that the earthquake could have potentially triggered the eruption. So obviously there's quite a growing number of observations of these kind of triggering events. The challenge really is that there's lots and lots of mechanisms that have been proposed on how you can actually get an eruption to be triggered. If you've got a magma body, you can squeeze it, so you can put a sort of a static stress change on it, squeeze the magma to generate your overpressure. You can do the opposite. You can cause a stress drop on the magma that can get bubbles growing, which can then cause an eruption. You can shake the magma, causing an eruption. So it's in that sense, it's kind of a non-unique problem. There's probably a mechanism out there that you could invoke to sort of get this triggering to occur. But what we kind of looked at the effect, what we did is to say, right, if we've got our magma body and we know roughly the overpressure in the dike, how much pressure do you need in the magma chamber to be able to generate that intrusion? So again, this is a fairly simple equation that basically links the excess pressure in the magma chamber that you need to cause the eruption or to cause a dike intrusion, the overpressure in your dike, and it's basically then just controlled by your ratio of, or the difference in your magma density to your rock density. And then you have this kind of this term on the differential stress on the end, but it's basically the tensile strength of the rock. So what we do, we plug in a bunch of different density contrasts, and we estimate for a given set of dike overpressures what the excess pressure in the magma chamber would need to be to drive that dike intrusion. So this, where the line going across is basically our guess of this particular intrusion, which was around 7.5 megapascal. And so for a reasonable range of density contrast and taking into some of the uncertainty in our estimate, then really a ballpark is that you need really a minimum of 2 megapascals of overpressure within your magma body to get the intrusion to generate. So what we did is we initially started with just getting some fairly simple static stress changes. So this plot is showing for different epicentral depths. So in this case, 9, 13, 17, 11, 15. And each one of these squares, different colors, is what the static stress change would be within the magma volume if the earthquake occurred in that position. And so if you look at where the earthquake actually happened down here to the south, and even if you take in some reasonable uncertainty, in terms of the static change, you never really get above a megapascal stress drop within the magma body. And remembering actually for the eruption to have happened, we actually needed a stress increase. So this is kind of actually acting in the wrong direction. Similarly, if you can we basically use the shake map to try and estimate the dynamic stress change, and doing the same thing in the area of the sort of magma body, which is kind of in here. Again, you're looking at maybe 1 to 1.5 megapascal stress drop rather than a stress increase. So in that sense, then it doesn't really, in terms of a static squeezing the magma, doesn't really work. But we have a stress drop. So what we started then to look at is, well, what happens if we take our magma batch and we apply a stress drop? What happens? And so there's been a number of studies showing that if you put a stress drop on your magma body, then you can basically promote bubbles to grow. And then as those bubbles grow, they themselves actually then cause a bigger overpressure and volume increase within your magma reservoir. So my colleague, this is what he did. We took an Ambrim-like basalt, and he ran these decompression models where, starting from an initial pressure, he basically just incrementally drops the pressure, and we looked at the volume increase of your initial melt source. And we do this for different temperatures and different water contents. So really the key is that if the magma is hot, so this is kind of shown in this blue line, what you can see is until you get a kind of a 5 megapascal stress drop on that magma body, you don't really get any bubble growth at all. If, however, the magma is a bit cooler, so down to sort of 1000 or 975 degrees, as soon as you have even a tiny stress drop on that magma, you start to get bubble growth almost instantaneously. Again, if you change the water content, so that's shown by these dashed lines, again, you see the similar effects. And in this particular case, even at cool magmas, but with lots of water, you actually need these huge stress drops to actually get them going. So the take home from this kind of plot really is that if it's too hot, you need too big a stress change to get the magma to grow any bubbles. However, we have a problem. As you cool your magma, it basically starts to solidify, and it gets to a point where if too many crystals grow, it physically can't flow anymore. So you just can't get it to erupt. And typically this is estimated to be around the kind of 30 to 40% crystal mark. And so that, again, that puts another bound on when these kind of eruptions can get triggered. So this plot is then showing your temperature along your x-axis and then the crystal fraction. And then these different lines are showing for different water contents, basically where these would track. And what you find is really there's this very narrow window of only around 50 degrees whereby your magma is hot enough that it doesn't get stuck, but also where you can actually apply a stress change to get bubbles to grow. And really the kind of peak temperatures around this kind of 970 to 980 degrees. Obviously you can come up to these higher temperatures, but by the time you get up to this kind of 130 degrees, you really need kind of 40 megapascal stress drops on your magma body to get any bubbles to grow at all. And so this really kind of points towards you need a slightly cooled down magma body, but not too cool so that it can't move any longer. So in terms of this particular case, what these models kind of look to show is, as I said, there's this kind of 50-degree temperature window where the magma is liquid enough that it can still flow, but where it can actually sustain a fairly small stress drop and get these bubbles to then over pressurize the magma system. And what it kind of implies is for, if you have a fresh intrusion of, say, basalt into your magma chamber, essentially it's going to be too hot to be able to get triggered by an earthquake, unless you have a huge, huge stress drop put sort of on it. One potential for that is then, if you look at globally where most kind of eruptions have been triggered, these are typically in arc settings. And the magmas in arc settings are more, at least based on this study, are more prone to being triggered than, say, in sort of more mafic regions or in central spreading ridges. But the caveat to that is obviously there's a lot more earthquakes in kind of arc settings along subduction zones than you get in these kind of back arc or in these kind of more mafic spreading ridges. So it could be an explanation as to why we see more triggered eruptions around arc settings. But that could also just be a bias because of obviously the number of earthquakes. So this is kind of to conclude that kind of initial jump, and then we're going to completely change topic. So in essence, then what we're hoping, or hopefully I've convinced you that, this at least gives a reasonable explanation or a potential method of how you can get these magma bodies to be triggered when they have, again, these kind of Goldilocks conditions. And it really hints that they need to be fairly primed before they can actually erupt from a triggering event. So changing tact completely. Oh, I'll get rid of that. New Zealand. So moving somewhat south. Here we have New Zealand. I've said, I'm sure Laura's, many of you have seen presentation by Laura looking at the tectonics of New Zealand, but as a quick recap, so we obviously have the North and the South Island. This is the GPS velocity field. That's been a sort of a long-term work of Laura's. And what you can see is on the North Island, you've got this rotation of the forearc into dextral strike slip towards the south of the North Island, which then propagates down into the South Island along the Alpine Fault. We're obviously dominated by the tectonics of, again, of the subduction of the Pacific plate beneath the Australian under the North Island. So this is the Hikurangi margin that obviously Laura's done extensive work on. And then when you come down to the tip of the South Island, you get kind of a reverse in subduction zone. So in the south, you've got the opposite case where you have the subduction of the Australian plate beneath the Pacific. And actually this southern area, this Fjorden region, is actually probably the most seismically active region in New Zealand. This is where we see sort of most of our earthquakes. But unfortunately, there's only around I think the last census showed there's only around 20 odd people actually live in that kind of area. So it's pretty remote and rugged terrain. So unfortunately, although it's one of the most seismically active, it's also not very well monitored. In the North Island, I said we're a very, New Zealand's a very interesting place to do tectonic studies. We've got a lot of things going on. So through the central North Island, we've got extension from this kind of rotation of the forearc, and this has led to the development of the Topol Volcanic Zone. And this is one of the most sort of rhyolitic, volume-wise, it's one of the most sort of prestigious volume generating of magma in the world, comparable with Yellowstone, and it's had numerous super eruptions over the last kind of 50 to 100,000 years. At the same time, we obviously, on the subduction zone, we get these sort of these diverse slip events from these kind of these deeper events beneath sort of the Wellington region, up to these kind of more shallow events that propagate right up towards the trench that sort of have been the sort of the focus of Laura's more recent work, where she's been offshore and putting down these kind of OBS and pressure sensors. If we look first at the Topol Volcanic Zone, so I said it's basically the result of this back arc extension that's then propagated along the Kermadec Ridge into sort of subaerial New Zealand. It's been active for around 1.6 million years, and there's a very well developed fault belt that runs through this the central North Island. If you, based on the block models of LoRa, if you look at the sort of the long-term wide-scale extension, then we're getting around 15 to 8 millimeters a year of extension from north to south, and you can see that in these sort of the overall trend of this, obviously the rotation. But what's interesting is that if you look at the aerial strain derived, again, just from GPS, as you can see, actually, the total volcanic zone itself has actually got some of the strongest contractional strain rates in the entire country. So this is kind of an enigma. So we've got an extensional rift zone, but it's contracting. If we look at, if we use the radar, then what we can, these are some examples from ALOS and ENVISAT, so some of the sort of older data sets. But what we actually see is around this kind of 20 millimeters a year of subsidence centered through that central volcanic zone. Now, bearing in mind, obviously, the extension, the long-term sort of large-scale extension is maximum really only probably 15 millimeters. So the fact that we're getting 20 to 25 millimeters of subsidence a year can't really be explained by the extension. So something else must be going on to drive this substance. And these rates are pretty high, and it's very long-lived. This has been going on for at least kind of 30 years. On top of kind of the broad scale deformation, we also then have, this is again the example of some of these geothermal fields where we get kind of 50 millimeters or more of substance a year focused on top of the geothermal where they're extracting. So one way that you can explain this is to assume that your substance at depth is being basically caused by contraction of magma. So as basically the magma solidifies and it becomes more dense, that leads to a volume change, which can then cause your substance above. If you do some, again, fairly simple models, then what we can do is we can estimate a volume of around 0.06 to 0.08 cubic kilometers per year of magma being cooled at depth. And that would give us this kind of a 20% volume reduction if you go from, say, a rhyolite into a granite. Again, you can play with some of the heat numbers, and you can more or less make it balance, that the amount of heat that is measured in the geothermal output can be explained by cooling off that amount of magma per year. What is nice is it fits very well with the magnetotelluric data. So we've got quite an extensive network of magnetotellurics that have been done along the rift zone, and where they see these conductive bodies does match up very much where we have sort of the peak subsidence. So this is our favorite explanation, is that we're seeing this kind of cooling of magma at depth. Now, what you might have noticed from, if I go back to this previous plot, is that over this particular time period, where your signal is dominated by substance, there is actually this uplift at this northern, so this is the Bay of Plenty, so there's some uplift at this northern coast, which you can just about see in this ENVISAT track. And when we took a better look, so we did because of some of the sort of coherence issues that I mentioned earlier, we do what's called a persistent scatterer technique. So this looks for more stable points on the ground surface, which can give you sort of, your basically act as kind of like mini GPS receivers. So they stay coherent permanently, and you can extract the information for your sort of long-term time series. The advantage in this for New Zealand is because of the vegetation, it means you do tend to keep coherence much better than elsewhere. So this again, in this bottom left plot is actually from ENVISAT. So this spans from 2003 to 2011. And what you can see is you obviously down to the south, you see the substance from on this cooling, but then you have this kind of up to around 1 centimeter a year of uplift on along this Bay of Plenty coast. Now, what's interesting is there's been no volcanism in that area for around 500,000 years. It actually sits outside of the active rifting. So the main rift zone is thought to step across into this region where we don't see much deformation. And so it's kind of in an unusual place. And so this is where this so-called these zombie volcanoes have been termed. So it's kind of a volcano that is seemingly dead, but has been showing signs of life. So I think some of these early work was from when people looked in South America at Laguna del Male, when they started looking at the radar and they started picking up these really big deformation signals that nobody really knew about. And this is essentially what we've done here. We've looked and we've seen this uplift, and then we've tried to look to see what could explain it. I think when we look back at the timing, so this is looking at these 3 GPS sites in the region. And what you can see is there's this fairly long-lived trend of uplift. And then when we come to this site, this RGMT, then what you can see is basically through, unfortunately, the data only starts in 2007, but what we can see is this kind of uplift. And then in 2011, it essentially, the signal kind of shuts off. And this is quite nicely shown in the northern component. And we see this in both the InSAR and the GPS, that we've got this kind of period of around 7 or 8 years where we see this sort of quite high rates of uplift, and then it more or less shuts off. The spatial pattern in itself is kind of what, for me, is what we kind of led to our interpretation that this was a magmatic source rather than some kind of tectonic flank related deformation. Is that if you look at the radial component, you can see this kind of this radial outward motion in the GPS, as well as then this uplift. And so what that pointed us to was, we believe that then this is being driven by some deep intrusion just off the axis of the main magmatic rift zone. And so that was kind of where we felt this was going. So what we do, we again, some very simple models. Unfortunately, because obviously with the position of the source, we've got very little constraint offshore as to what's going on. So we can't really say how far offshore the body may go. But in this case, we try different kind of simple kind of point sources versus sill inflations. And in essence, we get a best fitting model, which is around 19 by 20 kilometers in sort of size, inflating by roughly 20 millimeters a year over that kind of 8-year period. And this would be a 0.009 million cubic meters, or cubic kilometers rather, per year. Independently, there's been some work done, so by your very own Andrew Gase, looking at some of the seismicity or doing some active source modeling over the region, which also then does actually indicate these frozen sills at around 10 kilometers depth, which is what we're getting. So there's independent evidence suggesting that there are sort of these horizontally stacked magma bodies offshore. Another line of evidence is that during this kind of uplift episode, there was this sort of swarm of 3,000 earthquakes between 2005 and 2009, largely propagating offshore. So you can see the earlier events were inland, and then gradually they migrated offshore. Moment tensors for some of the bigger events are typically showing oblique normal faulting, again consistent with kind of in the sort of the rift setting. So what we did is to see if we've got this inflating body at depth, can that explain the earthquake swarm? So essentially what we do is, for each one of the earthquakes within the swarm, we take our best fitting sill model and we just do a very simple static stress change based on the sort of the epicenter of all of those individual events. And what we find is, we basically test the rake angle for those earthquake sources, and we look at how many of them fall into regions of positive or negative tensile stress. So yeah, just looking at the the Coulomb stress for our different sill and MOE bodies. And so what we found basically is for kind of basically normal or oblique mechanisms consistent with the swarm, we find that nearly around 98% of all of the events in that sequence would have been promoted to fail based on the inflation of this deeper source. So what our interpretation is that we've basically had a pulse of magma has come into a deeper storage zone just off the axis of the rift zone. That's caused this uplift and also then triggered off this earthquake swarm. when you look back at if you look at the GPS today, there's still slight uplift going on, but it's much reduced, kind of order of a few millimeters a year, as opposed to this kind of 10 millimeter a year. And so what we're inferring is that there must be these kind of repeated inflation events and potentially these seismic swarms that will kind of propagate offshore when we get these kind of renewed batches of magma get pumped into the system. And this is fairly consistent. There's been swarms in this area roughly every 20 to 30 years. So in the 1980s, there was a swarm in a similar location. Not quite as many earthquakes, but again, going forward, then hopefully if we do see some of these swarm events, it might give us an indication that we could start to see another sort of inflation episode. So the final hurdle, we'll now move to kind of looking at the broad scale tectonic motion for the whole of New Zealand that we've been trying to sort of piece together from basically combination of the InSAR and GPS. So really, how can InSAR help? So this is basically the evolution of the GNSS or GPS network through New Zealand. So this is just the continuous network. So you can see from in the 2000s, the network itself was pretty sparse. There was only an order of maybe 40 sites covering the entire country. Through, I think, a lot of work by John Bevan and Laura, the network really got pushed in the sort of the mid-2000s, but this has largely been focused along the Hikurangi margin. So this is obviously the subduction zone itself probably does pose the biggest kind of threat to New Zealand in terms of its hazard, which is why obviously they did focus a lot of the attention along the east coast and through the volcanic zone. And then from 2000 to 2019, there was some more growth, a few more stations in the South Island, but not many. And this is really the crux of the problem in the South Island, is that from a continuous network, you have very, very sparsely positioned sites. The Alpine Fault, for example, is forecast, or the best estimates of it, I think it's an 80% chance of rupture in the next 30 years. And yet, if you look at the GPS network, we're not really in a great position for measuring the deformation associated when that does rupture. The campaign data is another matter. There's around 900 campaign sites across the country. So that gives us a much better handle on the overall deformation. But again, the problem with those is the way the collection is done is that every 8 years, a different region of New Zealand is selected, and they go and they measure that region. Then 8 years later, that region will get measured again. The problem, obviously, with New Zealand is we've had quite a lot of earthquakes. We have these slow slip events. And so your temporal sampling is just not good enough from the campaign network to kind of isolate these kind of seismic events. If we look even since the last, so these are from earthquakes from 2003 onwards, it's been a relatively active period. So starting in the south, we had, there was a 7.2 in end of 2003. Again, we had in the 2007, there was a 6.7 earthquake again in Fiordland, as well as another one up in Gisborne. We had this Dusky Sound. Obviously, we've had the Darfield, the Christchurch. We had a sequence near Wellington in the 2013 period. And then more recently, obviously, we've had Kaikoura and this East Cape. In this plot, the red earthquakes where they were mostly offshore, so they shouldn't have too much impact, at least on the sort of deformation on the land surface, and also for some of their sizes. But if we look at this, the nice thing which we've been able to do is if we look at the MVSAT catalogue, with the exception of the Darfield sequence at the end of the MVSAT kind of operating period, we largely had a good chunk of time where we didn't really have any earthquakes to try and contaminate the interseismic velocity field. Going forwards, obviously, we're going to have an issue where Kaikoura has obviously completely changed the interseismic deformation field around the sort of central North Island. So this is just an example of the sort of early post-seismic deformation that we saw following Kaikoura, and some of this is obviously ongoing. So what we've done is we've basically looked at the sort of historic MVSAT catalogue that runs through this sort of kind of 2003 to 2011 period. And we've tried to then build a line of sight velocity field for New Zealand. Unfortunately, unlike the sort of Sentinel mission that flies today, which acquires images in both the ascending direction, so when the satellite's going north, and the descending when it's coming south, which gives you a better handle on separating horizontal and vertical deformation. ENVISAT basically only ever acquired in the ascending track. Unlike the data today as well, it tended to have much noisier orbit terms. And so it's generally a noisier data set and more difficult to deal with. But that's what to get that interseismic is kind of the best we felt we had. So we have to do some, I guess, some fudging, I guess is the probably best term for it. Is because obviously InSAR is only relative. If you try and correct some of these orbital ramps across your scene, if there is a long wavelength tectonic signature, which is obviously what we're looking for, when you do these corrections, essentially you can remove it. And so what we first do is we derive our InSAR deformation rates. So by forming multiple interferograms, we just solve for the best fit rate over that entire period. And then what we do is we subtract a model basically from the GPS, which gives us an indication of the horizontal component of the velocity field, and we remove that. Then we do all of our corrections, and then we add it back in at the end. With the idea is that then we're only stripping out sort of residual orbits and or some of the atmospheric terms. This is what we end up with. So on the left-hand side is basically the mean line of sight velocity field. And again, what's nice is you obviously see this overall right lateral shear across the Alpine fault through the South Island and through the dextral fault belt. And I said, this is to get, because we've only got the one look direction, essentially to actually extract the vertical from InSAR itself is essentially impossible. So what we've done is to make the assumption that the horizontal velocity field from the GNSS is good enough to say that's what the horizontal deformation is. And so if we remove that from the InSAR observations, then in theory, what's left over there'll be some noise terms in there, but it should also be representative of the vertical signal. And so that's basically what's plotted on the right-hand side, is where we've stripped out the horizontal components of the eastern and north velocities, and then just looked at the residual. The colored dots are GPS, which we're collecting data at the same time. And so for the most part, it actually does a pretty good job. So across we obviously in the central North Island, you can see the substance from the TVZ that we talked about earlier, and then this little bit of uplift. And then we see this fairly widespread substance across the east coast of the North Island related to the ongoing subduction. And then the top of the South Island, we also see this kind of lower levels of substance. Across the rest of the South Island, the data is definitely a bit noisier, and we do have some of these issues where, although we're making the assumption that everything left over is the vertical, it will also include things like residual atmosphere or any other noise terms that we've not managed to remove. And so there are certain spots where it doesn't do so well. In part, the worst case actually, when you look in some of the InSAR data on the leeward side of most of the mountain belts in New Zealand, because of the wind direction basically comes from the northwest. And so what we find is you get these kind of very, very impressive looking deformation signals that are caused by these atmospheric lee waves as you get eddy currents form over the mountains. And so we see this across basically huge swaths of the South Island and also on the North Island on this eastward side. And these are really, or more or less impossible to deal with because weather models are too coarse. So they just can't capture that kind of spatial variability. So yeah, this is still an ongoing challenge, and certainly signals like this will definitely be still probably be present in our estimates. On top of that, I alluded earlier, we also have kind of some of these anthropogenic problems. So we've also got geothermal that add additional noise. In the South Island, we've got landslides everywhere. And unfortunately, a lot of because of the technique we've had to do, a lot of the scatterers that we use or on the mountain at least, or on the downward facing slopes of the mountain. And in many cases, these are actually sliding. So this actually causes, even if they're uplifting, we are actually seeing a sort of a net subsidence, which, yeah, does make things more complicated. Similarly, we also see in some of the glacial valleys, this is an example of around 6 to 7 millimeters of subsidence over that time period. And we think it's the compaction of the sediment load within the river after the river channel's been abandoned. So this is the current outflow of the from the glacial dam. And where we see the peak subsidence is actually in these old river terraces on the periphery, which we think are then just contracting. The problem is then when we try and build our vertical estimate of the velocity field, is these kind of localized signals, because of our scarcity of points, then they basically bias our sort of long wavelength estimate. And this is kind of shown in some of these profiles. So if we take a profile across the Southern Alps, you can see these red triangles are the GPS uplift rates of around 4 to 5 millimeters a year. But what you find is when we get into the mountains, the InSAR is actually showing subsidence. And that's basically that effect of these compaction sources. So when I average over the region, it just pulls down our solution. So what could really be going on, and what I'd hope is that what the InSAR should show is something more like this, where we've actually got this uplift trend, but it's going to be very difficult to tease out, at least from this existing catalog or data set. Moving north, if we come across the Kaikoura region, we can see that we've got this subsidence along the coast of around 3 to 4 millimeters a year, which then dies back as you move inland, and then with similar profiles going from north to south. What's interesting is this case for Kaikoura is that one of the sort of ongoing aspects of the earthquake is how much the subduction zone was involved. And there were some previous studies that suggested that there was basically the area beneath Kaikoura was permanently locked and couldn't sustain slip. However, this data and some of the locking models that Laura's done do suggest there must have been some partial locking along this coastline, which again is causing this kind of subsidence. Further north, again, we see the same overall patterns. Hawke's Bay is an interesting one. We see this very localized deformation just inland. Some of this is also some anthropogenic water pumping, but also it indicates there's there may be some kind of local heterogeneity on the subduction zone. So getting close to the end, what we've done is we've basically taken this data set, and for an independent project, what we've been looking at is for sea level rise. So the effects of actually including vertical land movements on projections of future sea level. So what we essentially do, we basically extract a strip around the coast to generate a kind of an estimate of the long-term vertical rates. So in New Zealand, around 250,000 people live within 2 meters of the high tide mark. And estimates are suggesting that our major urban centers, so Auckland and Wellington, will be lots of the houses which are obviously along the coast will become uninsurable because of flood risk and sea level rise problems. And obviously in many areas, the vertical land movement only sort of compounds this issue. So this is just 2 examples. This is on the East Coast, showing 2 nearby sites and just showing the effect of where you include sea level rise. And what the InSAR is really good for is because we've got this high spatial resolution, these 2 locations are only around 6 kilometers apart. But what you actually find is because of this local tilt, you actually find that in one area of so in this case, the beach, the northern end of the beach in Napier will have around 1.3 meters of sea level rise by 2160, whereas you come south and it's around half a meter less. And that's purely because of the vertical land movement. It's not straightforward. New Zealand, obviously, it's very dynamic. And if you look at, we've obviously done it for the interseismic period. But if we have another earthquake, then obviously our estimates completely get blown out of the water. So as obviously examples, so if you look at this uplift in the Bay of Plenty, that obviously is now stopped. And so in this particular estimate, then obviously what we'll end up doing is we'll overcook, we'll underestimate the sea level rise in areas where we're seeing these periodic uplift signals. And similarly, if you come to like Kaikoura uplifted by between sort of 3 and 8 meters during the earthquake. And so for them, probably the vertical land movement now has kind of become, it's not a problem any longer. They've got plenty of extra room on land to not have to worry about the sort of 2 millimeters of subsidence that we were seeing before the earthquake. So going forward, how in dynamic settings we can actually best use these kind of data is going to be a challenge, and may involve having to do kind of some of the earthquake simulators and trying to do some more probabilistic estimates of where the long term is truly long term versus where we're going to see these kind of dynamic changes. So I'll finish off there. So hopefully you've seen, InSAR is obviously a powerful tool. It's not without its faults, but it can be a very powerful tool for monitoring deformation on a range of temporal and spatial scales. I would argue that some of the old archive mission data is kind of neglected now, because obviously we do have these huge wealth of data coming through. But in some areas, actually, I think the older data is worth looking back at, because it can provide some useful constraints. The InSAR certainly pulls out lots more spatial heterogeneity in terms of the bulk deformation field. So we're seeing a lot more variation in the vertical that we didn't really know about before. And the capability is improving. Right? We've got more and more sensors getting launched. Obviously, InSAR will be launched maybe next year or the year after. And so we're going to have more and more data to be able to deal with, and to be able to hopefully look at all these different problems and open up a real wealth of data for people to look at. And I think, yes, and I shall leave it there.
Thanks, Ian. Really nice talk. Let's see whether there are any questions from the audiences. If you have any questions, you can either like unmute yourself and ask the question, or you can type it in the chat and I can ask it for you. Either way is okay. Harm, I see you have your hand up. Yeah.
Sure. Thanks, Ian. It's a great talk. I have a question about the South Island, and maybe this is a matter of the density of the GPS network, but I think what you showed across the Southern Alps, for example, in the Franz Joseph area, maybe an uplift rate in the Southern Alps on the order of 5 millimeters per year. What I remember, my information may be a little bit dated on the constraints, is that that the exhumation rates were on the order of 8 millimeters per year, or maybe 10 millimeters per year, based on fish and track data. Is this a difference in resolution, or do you think that there is a substantial difference between these two data sets?
There's certainly, I think there is definitely a difference. I don't know whether some of the GPS where the sites are located, a few of those have had issues where they're sitting on, in some cases actually they were sitting on the top of a landslide. So that's probably biasing slightly down the estimate. And also, if you look at some of the time series of the GPS there, because of the ice load, you get these very, very strong seasonal transients, which obviously you do your best to try and remove those. But potentially, if you get a slight incorrect correction, then you could also then affect. So for me, I would say, based on the two measurements, although there's a difference, I'd say based on the errors, I would say they're fairly consistent.
Thank you.
Any other questions? I actually have a question I can ask, maybe taking advantage of being the host. So you talked about the mechanism of how these are the volcanoes are getting triggered by the nearby earthquake. But is there any effort on that, like to rule out other possibilities, like other earthquakes, like delayed mechanism, or even maybe the volcano is already due, such kind of possibilities?
Yeah, and that's where it's tricky, right? Because it could have been that the earthquake, the earthquakes are just a complete coincidence that even though the magma was sat there, that it got to a point where it was able to erupt without necessarily having any external forcing. So I certainly, I've always been very dubious of triggering.
But how far, like in back, can you date like earlier records? And is it happening at the right time, or
Yeah, so there's a study that was done on global sort of triggering estimates, and it varies. So in some cases, they argue you can have up to like 3 years in advance from a static change. So I guess that's the big difference. Is in this case, I think probably it was dynamically triggered. And again, the timing works. So the time of the earthquake was around 30 hours before. And if you look at some of these dike evolution models, they kind of work. But elsewhere, yeah, there's been a big earthquake, and then 3 years later, an eruption's happened. And if people have gone back and said, well, the static change in the sort of volcanic system would have been primed to fail. But yeah, I don't know, I guess the longer the time period you push out, the more dubious I'd be that it's just, it's not necessarily a coincidence.
Okay, Alec, I think you're muted still.
Can you not hear me?
Yeah, we can hear you now.
Okay. I think thanks for the talk, Ian. I think actually my question was pretty related to that last one. I was going to ask about the earthquake triggering and about whether I was quite interested in the idea you need these specific conditions for a triggering process to occur. And I was wondering how the length between the supposed earthquake and the trigger, whether that affected the need for these specific conditions. So I guess kind of related to the previous question, if that makes sense.
Yeah, so in this particular, I think, in this particular case, because the timing was quite close by, so I didn't actually, if I just go back. Where are we? So yeah, let's grab that. So these are, can't really see. So Eleonora Revolta, Potsdam has done some modeling on basically the evolution of volume within the dike intrusion and how it evolves with time, and basically shows you get this this kind of growth scale, which is an exponential sort of growth rate. And again, there's these timings that they've got from sort of intrusions in Kilauea, Afar, and so on. And when we initially looked at this, and again, whether it's coincidental, is that the time of the eruption after the earthquake is around 30 hours. And when you do these kind of dike evolution volumes, it more or less works that if you had an initial stress drop that then triggered the eruption, you could then get the dike would have enough time to grow into its kind of final state. So that hinted to us that could be, again, an additional causality, or pointing us towards it being a causation rather than a coincidence. But certainly, I think when you do some other of the tests, if the earthquake, you don't have to move the earthquake very far, and it basically would have very little effect in terms of at least the static stress. Or if you move it closer, then you could get these really big stress drops. And for us, I think in the absence here of any other, we don't see any other way that the magma could have potentially been overpressured to drive the eruption. Whereas, obviously in other cases, you may have some deeper intrusion. And in fact, here we could have had a deeper intrusion that we just don't see, that it's primed the system by magma injection, but we just don't have the resolution to detect it.
All right. I still have a couple of questions, but I guess I can send you emails later on. We are running a little bit over time here. So thank everybody for staying tuned, and we'll see you guys next week. Thanks, Ian.
Yeah, thanks very much.